Okay, in the last video we talked about how moving electric charge creates a magnetic field. So whenever you have moving electric charges, the magnetic field created by that charge can be affected by another magnetic field. So say for example the Earth's magnetic field. Any moving electric charge coming past the Earth can be deflected by the Earth's magnetic field. And we do have a lot of moving magnetic or electric charges coming from the sun. So we have all of these charges that are entering into the Earth's magnetic field and being deflected to either the north or the south. And it's these charges coming into the Earth's atmosphere and interacting with the atoms in the atmosphere, causing them to gain energy, get excited, and give off light that creates the auroras. The aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere. We don't really get to see the auroras here in Vancouver, but if you were to head up north, you would see, especially in periods when there's a very high solar activity, these fantastic light shows in the night sky. And this is electric charges interacting with atoms in the Earth's magnetic field and creating a light show in the atmosphere when they strike the atoms. So we get these fantastic light shows. These are static images, but there's great videos on YouTube, and I've put some of them on the website of the auroras, and they really do kind of shimmer and move around. There's a fantastic one that was shot from the International Space Station. So you get a view of the aurora from above, which is not what you usually see. So whenever we have a moving electric charge, it can be affected by an external magnetic field. So it experiences a force. And we're going to have another right-hand rule. Another right-hand rule. So this is going to be right-hand rule number 2. And we use this to determine the direction of the force on a moving electric charge. So first thing we're going to do is we're going to point our fingers into 3 directions. So I often like to call it the 3-finger rule. You'll see some textbooks which call it the right-hand rule, and they just use their thumb and their fingers and the palm of their hand, or they use their thumb, the fingers like this. I'm going to use these 3 fingers. So your thumb, you point in the direction of motion. So this is the direction of motion. The way I always like to remember it is if I'm hitchhiking, I always point my thumb in the direction I want to move. Hitchhiking is not a very good idea though, but if I was hitchhiking, that's what I would do. Then your first finger, this always reminds me of a gun, right? Guns go bang, B for bang. This must be then our magnetic field. So I point my first finger in the direction of the magnetic field. And then my middle finger, well, my middle finger is of course my F finger, right? My F for force. So this is the direction of the force on the charge. So we have our thumb pointing in the direction of the motion, or if you like, in the velocity, the direction of the velocity. My first finger in the direction of the magnetic field, and then my middle finger in the direction of the force. So as long as I point my fingers in the direction according to those 3 vectors, I can always find either the direction of the force on the charge or the direction of the magnetic field that it must be traveling in. So a quick example, suppose I had a magnetic field directed into the page, and I had a positive charge moving in this direction. So that's the direction of V. The magnetic field is into the page. So I use my right-hand rule, and I find that when this electric charge gets into this region where there's a magnetic field, it experiences a force in this direction. Okay, so magnetic charge moving in that direction and a magnetic field into the page experiences a force upwards. There's lots of great examples in the textbook of using this right-hand rule. One thing I want to point out, it's always funny to see students doing these questions on a test because they end up trying to twist their whole body around. One thing you can do is you can always take the page that you're trying to look at and rotate the page so that you don't have to twist your arm to meet the orientation of the page. Okay, so that's our right-hand rule. That tells us the direction of the force. What about the magnitude of the force on that charge? Well, that's given by this equation. I take the magnitude of the charge, multiply it by the velocity, and the magnetic field. So this will tell me the magnitude of the force on the charge. Now, one thing that you have to keep in mind is that only the perpendicular component of the magnetic field causes any force. Note that all three fingers are at right angles to each other. They have to remain at right angles to each other because we only want to use the perpendicular component. So sometimes you may have to add in a sine theta or a cosine theta to this term to determine only the component that is perpendicular. So this will tell me the force in newtons. Now obviously if an electric charge experiences a force pushing it upwards, what's going to happen is the path of this electric charge, which was in this direction, will start to change. And as it starts to change, the direction of the force also changes. And what happens is these charges can be deflected into a circular path. So now we also have circular motion. So again, what's happening is this force here, QVB, is causing centripetal motion, mv squared over r. We have v on both sides of the equation, and we get q times b equals mv over r. So now depending on the mass of the charge, the magnetic field, the speed, and the orbital radius, the radius of this circle, we can find any unknown in this equation. And it's actually this type of calculation that people did to determine a lot of the masses of our subatomic particles. They're obviously things that we can't take and weigh on a scale. We've determined their mass through calculations like this. Same thing is true for a wire in a magnetic field. So here I have a current going into the page in this direction. That current has a circular magnetic field. Remember our first right-hand rule. So it has a circular magnetic field. So the magnetic field created by this wire could also be affected by this magnetic field outside. Same thing, right-hand rule. I point my thumb in the direction of the charges, so they're going into the page in a magnetic field pointing to the right, so they experience a force acting downwards. So you can see the magnitude of the force on this wire is down. So same right-hand rule, but we're just changing it to a whole current of charges rather than a single charge. Now the magnitude of the force on this wire is the magnetic field times the current times the length of the wire. So L is the length of wire that's in the magnetic field. Again, only the perpendicular component of the magnetic field causes any force. So here they're nice and perpendicular, but you have to keep in mind that you may have to add in a cosine theta or a sine theta to this term. So because a wire can be affected by a magnetic field, that's the basis of every electric motor. Here I have a loop of wire in an external magnetic field that points in this direction. So as the current is traveling around this wire in this direction here, the current going into the page in a magnetic field that way experiences a force upwards. On this side of the loop, it experiences a force downwards. So one side is being lifted up, the other side pushed down. That causes the rotation here of our electric motor. So by having a current going through a wire, a loop of wire, in a magnetic field, we get a rotation. And that's a basic electric motor.